Hello everyone, we're back to this week's business statistics tutorial. I'm Lucy and in today's tutorial we're gonna cover chapter 10, correlation and regression. This chapter introduces two very important statistical tools that we widely use in business, economics, finance, marketing, and any other fields. Whenever a business wants to understand whether two variables are related, for example, whether increasing advertising spending leads to higher sales, whether customer satisfaction affects repeat purchases, or whether study hours influence scam scores, they often begin with correlation. Once they know a relationship exists, they can then use regression to predict future outcomes. So in today's tutorial, we're going to learn 5 main ideas. First, we understand what correlation actually means. Then, we'll learn about how to interrupt the correlation coefficient, which is represented by letter R. After that, we'll introduce the regression equation and see how it's used to make predictions. We'll also discuss the coefficient of determination, which tells us how well our regression model explains the data. Finally, we'll briefly introduce prediction intervals, which help us understand the uncertainty behind predictions. One concept that I really want everyone to remember through this chapter is this: correlation does not imply causation. Just because two variables are related doesn't necessarily mean that one causes the others. This idea appears frequently on exam, so we'll spend some time discussing it later in tutorial. Alright, let's start with our first topic. What is correlation? Now let's begin by answering a very classic question. What is correlation? Correlation is a statistic measure that describes the relationship between two quantitative variables. The key word here is relationship. It tells us whether two variables tend to change together. It doesn't tell us that one variable causes the other. It simply tells us whether they are associated. Let's look at a few business examples. Suppose a company wants to know whether spending more money on advertising is associated with higher sales. Or imagine a professor wants to see whether students who spend more hours studying generally earn higher exam scores. Another example might be whether years of work experience are related to annual salary. In opposite situations, we're interested in understanding whether two numerical variables move together, and that's exactly what correlation helps us measure. Now, correlation has two important characteristics. The first is the direction of the relationship. A relationship can be positive or negative. A positive correlation means that as one variable increases, the other variable also tends to increase. For example, if students spend more time studying, their exam scores generally increase as well. Similarly, companies that invest more in advertising may also see higher sales. On the other hand, a negative correlation means that as one variable increased, the other tends to decrease. A common business example is the relationship between price and demand. As the price of a product increases, customers often buy less of it. Another example is the relationship between driving speed and travel time. If your speed increases, the amount of time needed to reach your destination usually decreases. The second characteristic of correlation is the strength of the relationship. Sometimes two variables are very closely related, other times the relationship is much weaker. Later in this chapter, we'll use the correlation coefficient, R, to measure exactly how strong the relationship is. Now here's the most important idea on this slide, and honestly, probably one of the most important ideas in the entire course. Correlation only tells us that two variables are related. It does not explain why they are related. For example, imagine we observe the ice cream sales and the number of people visiting the beach both increase during summer. Does buying ice cream cause people to go to the beach? Of course not. The real reason is that the hot weather causes both of these things to happen at the same time. That means there may be another variable, sometimes called the lurking variable or confounding variable, that explains the relationship. So whenever you see the word correlation, don't immediately think cause and effect. Instead, think it as an association between two variables. We'll spend more time on this idea in the next section because it's one of the most frequently tested concepts in this chapter. Before moving on, here's a quick question for you to think about. If study hours and exam scores have a positive correlation, does that prove that studying more always causes higher grades? The answer is not necessary. Many other factors such as previous knowledge, attendance, sleep, or motivation could also influence exam performance. That's why we must always be careful about interrupting correlation. Now that we understand what correlation is, let's look at how we actually measure it using the correlation coefficient, R. As we already understood what correlation is, the next question is, how do we measure it? To measure the strength and direction of a linear relationship, we use a value called the correlation coefficient, which is represented by the letter R. The value of R is always between -1 and +1. That means it can never be greater than 1 or less than -1. The sign of R tells us the direction of the relationship. If R is positive, then two variables tend to move in the same direction. As one variable increases, the other generally increases as well. For example, study hours and exam scores usually have a positive correlation. Advertising expenditure and sales revenue are another common example. If R is negative, the variable moves in the opposite direction. As one variable increases, the other tends to decrease. For example, as the price of a product increases, customers' demand often decreases. And now let's talk about the magnitude or the size of R. The closer R to +1 or -1, the stronger the linear relationship. For example, R equal to 0.95 indicates a very strong positive linear relationship. R equal to -0.95 indicates a very strong negative linear relationship. On the other hand, values closer to 0 indicate weaker relationship. For example, R equal to 0.2 suggests a weak positive relationship. R equal to -0.15 suggests a weak negative relationship. And if R equals exactly 0, it means there's no linear correlation between the two variables. Notice I emphasize the word linear. This is an important point because many students misunderstand what R equal to 0 actually means. R equal to 0 does not necessarily mean there is no relationship at all. It only means that there is no linear relationship. The correlation coefficient only measures the linear relationships. Another common mistake on example is focusing only on the sign of R. Suppose we have two values. R is equal to 0.85 and another R is equal to -0.85. Which one represents the stronger relationship? The answer is neither. They have exactly the same strength because they have the same absolute value. The only difference is the direction. One is positive and the other is negative. So whenever you're interrupting R, always ask yourself two questions. First, is the relationship positive or negative? Second, how strong is the relationship? The correlation coefficient C is only appropriate when we are studying quantitative variables and when relationship is approximately linear. If that scatter plot shows a curved pattern instead of a straight line trend, the value of R may not accurately describe the relationship. So before calculating or interrupting R, it's always a good idea to look at the scatter plot first. In summary, the sign tells you the direction, the absolute value tells you the strength, and R only measures the linear relationship. These are the three key ideas you should remember about correlation coefficient. Now that we know how to measure correlation, let's move on to one of the most important concepts in the chapter: why correlation does not imply causation. Now let's talk about one of the most important concepts. You often hear people say, these two variables are highly correlated, so one must be causing the other. However, this conclusion is not always correct. Correlation does not imply causation. Let's first understand the differences between these two words. Correlation simply means that two variables are associated or tend to change together. Causation, on the other hand, means that one variable directly produces a change in the other variable. These are two very different ideas. Just because two things happen together does not mean that one causes the other. Let's look at the example from the lecture. Suppose researchers discover that towns with more movie theaters also tend to have more homicides. Based on this information, someone concludes building more movie theaters will cause the homicide rate to increase. Is that conclusion correct? The answer is no. This is a classic example of confusing correlation with causation. The real explanation is probably the larger cities naturally have more people. Because they have larger populations, they also tend to have more movie centers, more business, more traffic, and unfortunately sometimes more crimes. In this case, the hidden variable is population size. So population influences both variables. The movie theaters themselves are not causing crime. This type of hidden influence is called a lurking variable or a confounding variable. A confounding variable is an outside factor that affects both variables and creates the appearance of a relationship. This idea is especially important because many exam questions are designed to test it. Whenever you read a statement like, there's a significant correlation between X and Y, ask yourself this question: does the information only describe a relationship, or does it actually prove that one variable caused the other? Unless the question specifically describes a well-designed experiment, the safest answer is correlation alone does not establish causation. So before we move on, let's summarize the key points. Correlation describes a relationship between variables. Causation means one variable directly affects another. A lurking variable may explain why two variables appear to be unrelated. Never assume cause and effect based only on a correlation coefficient. If you clearly distinguish these ideas, you can avoid one of the biggest mistakes students make in this chapter. Now we understand what correlation is. Let's move on to another important topic, regression. Also, correlation and regression are very closely related. They answer different questions. Correlation tells us whether two variables are related and how strong that relationship is. Regression goes one step further. It allows us to predict the value of one variable based on another variable. For example, suppose a company has collected data on advertising spending and sales revenue over the past year. If they know that these two variables have a strong positive relationship, they may want to answer a practical business question. If we spend another 1,000 on advertising next month, how much can we expect sales to increase? Correlation alone cannot answer the question. Regression can. That's why regression is widely used in business, forecasting, finance, economics, marketing, and data analysis. The equation of a regression line is written as y cap is equal to a plus bx. Let's break down each part of the equation. First, the symbol y cap, pronounced y hat, represents the predicted value of y. Notice this not the actual observed value. It's simply our best estimate based on the regression model. Next, A is called the y-intercept. The intercept is the predicted value of y when x equals to 0. Depending on the context, this value may or may not have a practical meaning. For example, suppose X represents years of work experience. Does having 0 years of experience always make sense? Sometimes yes, sometimes no. So while the intercept is always part of the equation, we should be careful when interpreting it in real-life situation. The second number b is called the slope. It tells us how much the predicted value of y changes when x increases by 1 unit. Suppose our regression equation is y hat is equal to 20 plus 5x, where the slope is 5, the intercept is 20. It means that for every 1 unit increase in x, the predicted value of y increases by 5 units on average. So the increasing advertising by one campaign is associated with increase about 5,000 in predicted sales. Notice we use the phrase predicted increase or expected increase. Regression gives us an estimate. It does not graduate that every future observation will follow the equation exactly. In reality, actual data points are usually scattered around the regression line. Some observations fall above the lines, others fall below it. That's completely normal. So remember why R only measures the strength and direction of the relationship. It cannot be used to calculate predicted value. Only regression equation can do that. The second mistake is making the predictions far beyond the range of the initial data. This is called extrapolation. For example, imagine all of your origin data has x value between 5 and 20. If someone asks you to predict y x equal to 100, the regression equation will still produce an answer. But the answer may not be reliable because the model has never observed data anywhere near that value. To summarize this slide, regression helps us predict one variable using another. The equation is y hat equal to a plus big X. The intercept tells us the predicted value when x equal to 0. The slope tells us how much y hat changes for every 1 unit increase in x. And finally, remember the regression provides an estimate, not an exact answer. Now let's know the regression equation and learn how to use it to make predictions. For example, if we have a line that y hat is equal to 3x, and we are asked to predict value of y/x is equal to 2.5. To solve this problem, we simply replace x with 2.5. So y hat is equal to 3 multiplied 2.5, which equals to 7.5. So the best predicted value of y is 7.5. We are finding that value that our regression model predicts. The actual observation could be higher or lower because real data always contains some variabilities. The regression line simply gives us the best estimates based on the available data. So just remember, use the regression equation, not the correlation coefficient, to calculate the expected value. Simply substitute the given x value into the equation and avoid extrapolation beyond the data range. And let's introduce another important statistic called the coefficient of determination, which is written as y squared. Many people wonder, if we already have the correlation coefficient r, why do we need to calculate r squared? So the answer is that r and r squared tells us different things. The coefficient r tells us the strength and direction of a linear relationship. However, r squared tells us how well the regression model explains the variation in the response variable. It tells us how useful our regression model is. So if r is equal to negative 0.7, this question asks us to find the coefficient of the determination. So we simply square the r. So r squared is equal to 0.52 or approximately 52. So it shows that the percent of variation explained by regression line. So that means 52% of the variation in the dependent variable y can be explained by this linear relationship with x. The remaining 48% of the variation is explained by other factors, random variations, or variables that are not included in our model. So the key point here is that we just simply square the correlation coefficient to calculate the coefficient of determination, and the negative sign disappears after squaring because every number after squared is positive. So a higher r squared still does not prove causation, but it generally indicates a better fit of our model to the real statistic. Finally, let's talk about the prediction interval. For example, if the regression equation tells us the predicted value of y is 9, does that mean the actual value of y will definitely be 9? The answer is no. Remember, regression equation only gives us the best estimate. Real-world data almost never falls exactly on the regression line. So that's why we use something called a prediction interval. It gives us a range of values that we expect a future individual observation to fall, with a certain level of confidence. In today's lecture, the confidence level is always 90%. That means if we repeatedly collect similar data and calculate prediction interval, we would expect approximately 90% of those intervals to contain the actual future value. Notice that we are talking about intervals, not individual predictions. Instead of saying the predicted value is exactly 9, we're going to say we are 90% confident that the actual value will fall behind 6.8 and 11.2. This is much more realistic because real observation always contain random variation. And let's summarize the steps for solving a prediction interval problem. Step 1, using the regression equation to calculate the predicted value. Step 2, use the standard error and the confidence level to calculate the prediction interval. Step 3, interpret the interval in complete sentence. Finally, here are some common exam mistakes. The first mistake is porting only the predicted value and forgetting the interval. If the question specifically asks for a prediction interval, a single number is not enough. The second mistake is writing the interval incorrectly. Always report both the lower limit and upper limit and include the correct confidence level into interpretation. And finally, remember a wider prediction interval means that there's more uncertainty in the prediction, while a narrower interval suggests that the prediction is more precise. That brings us to the end of the new concept in this chapter. Before we finish today's tutorial, let's have a moment of reviewing the key ideas from this chapter. Today we learned that correlation helps us describe the relationship between two quantitative variables. Are the variables related? If they are, how strong is the relationship? To measure this, we use the correlation coefficient represented by R. Remember that R always falls between -1 and +1. The sign tells us the direction of the relationship. A positive value means that the variable tends to increase together, while a negative value means one variable increases as the other decreases. The absolute value tells us the strength of the linear relationship. Next, we discuss one of the most important ideas, that is, correlation does not imply causation. Whenever you see a correlation question in the exam, be careful not to confuse association with cause and effect. So, unlike correlation, regression allows us to predict the value of one variable based on the other. We learn about the equation, which is y hat is equal to a plus bx. And to make a decision, we simply substitute the given value of x into the equation. We also learned the coefficient of determination, or y squared. Remember that it tells us how much the variation in the response variable is explained by regression model. And the prediction interval gives us a range of possible numbers for our future observation rather than just one predicted number. Because real-world data always contain variations, prediction interval helps us understand the uncertainty behind our prediction. Before we end today's tutorial, I'd love to leave with a few exam tips. So, first, always read the question carefully and identify exactly what it is asking. Is it asking you to interpret the correlation coefficient, to calculate R-squared, to make a prediction using the regression equation, or to explain why correlation does not imply causation? Understanding the question is the most important step. Second, don't just memorize formulas. Try to understand what each status actually means. And finally, I encourage you to practice as many questions as possible. Correlation and regression are topics that become much easier once you have worked through several questions. Thank you for watching today's tutorial. If you have any questions, feel free to join the Tuesday's tutorial session from 1 p.m. to 2 p.m. or post your question on Slate. I hope this tutorial helped you better understand correlation and regression, and I will see you in the next tutorial. Have a good day, everyone. I'm Lucy and John. I'm always here to help you.